Lesson 106, pretty intensive lesson. This is one of two videos for lesson 106. In this lesson, I want to go over really the first time we directly dealt with Ohm's law. Okay, and there's going to be one aspect in particular towards the end of this that's very important. You're going to see it time and time again. What happens if we operate a resistive load at a voltage other than its rated voltage? What happens to the other values? And we're going to use Ohm's law to find that out. So anyway, beginning of Ohm's law, an intro to Ohm's law. Usually when you deal with this, you're going to look at what they call the Ohm's law wheel, which this is an example. This is all throughout the textbook, easily found online. Copy this somehow into your notes. I'm not going to tell you to memorize the thing because frankly I don't have it memorized, but you will need to at the very least reference this or memorize some of the key equations. So, kind of the moral of all this here, or why do we need to know this? Basically, if we're given any two values in a electrical circuit, we can calculate the other two unknown values by using Ohm's law. We must be given two values, or we must know two values. So if it's real world, you must be able to determine two of the values. If it's an equation, they've got to give you two values to start. Otherwise, you can't go anywhere. You need two to begin. But we can use those two combined with Ohm's law to find the other unknown values. Okay? So the way this works, we first need to determine what are we looking for. If we're looking for watts, we're going to go to the watts sort of quadrant, if here. So you look in the middle and it's got the P for watts. That tells us that in this case, the pink section is the watts quadrant. So if I'm looking for watts right away, I'm going to that section. Okay. If they give me the next thing, what two values have they given me? If they've given me volts and amps and I need to find watts, that's the equation we're going to use, V times I. If they've given me amps and ohms, that's the equation we're going to use, I squared times R. And if they've given me volts and ohms, that's the equation we're going to use, V squared divided by R. So you can see no matter what combination they give you, there is a calculation we could use to find our watts value. And naturally, you can expect to see the same thing now if they give me amps. Now I'm over here in this yellow amps quadrant. And I'm not going to read through every equation once again, but you can see there is an equation for any combination that we would have, right? And now, this is a great one, for example, the square root of P divided by R. Sure, we could do that. That equation is a little messy, right? I mean, you got a square root involved there. You're going to find 9 times out of 10, you can sort of manipulate the information and data and calculate things in certain ways. And we can avoid those types of equations pretty handily, and there's an example of what I mean by that coming up. But 9 times out of 10, you're going to find yourself avoiding these square. At least I do anyway. They're just, to me, not friendly to work with. And sometimes you have to. There's no way around it. But anyway, we have the ohms quadrant here once again. No matter what combination, we have an equation that will help us find ohms, no matter what two values we're given. And just to round things out with volts, same story. We can time I times R, P divided by I. And there again, we've got that square root scenario as well. So, sounds great. Let's look at an example here of what we're talking about. So here we have this circuit they're going to tell us is 120 volts, 100 watts. Okay, great. How many amps and how many ohms is that going to be? Well, we can figure that out pretty easily because they've given us two values. We'll look at Ohm's law, find the other two values. So let's go ahead and try to find amps to begin with, okay? We don't know what the amps are. Let's start there. It doesn't really matter where we started. We could have just as easily started with ohms. Start with amps. We're looking for amps. We're looking in the amps quadrant over here, the yellow section. We know, of course, volts and watts. So which equation are we going to use? Well, this P divided by V section. And funnily enough, this, in my opinion, this wheel actually combines, how we said volts could be I or V, watts could be P or W. In my opinion, they're almost interchanging between the values. Here they reference, volts as V. That would relate to amps as A, but they actually use I in this case for whatever reason. So again, you just quite simply need to be well versed in either way, right? So anyway, back to the point. P divided by V, watts divided by volts, right? So we'll take our 100 watts, divide by 120 volts, and of course that gives us 0.833 amps. Okay, that was, pretty easy with that Ohm's law wheel, no big deal. So let's file that up here. Maybe we can use that later, right? In fact, we're going to use it here on this next step. So the only other value we don't have is ohms. So we're going to go to the ohms quadrant of the Ohm's law wheel. Now, if I wanted to go back and use my original volts and watts that I have to use V squared divided by P. Maybe we can avoid a squared function if we wanted to, right? And we can do that because now we actually have three values. So again, if we were to use the original values that we were given, volts and watts, we'd have to do V squared divided by P. I don't feel like doing a squared problem right now. So let's go ahead and use the amps that we've already calculated, right? We can use those two values, volts and amps in this case, to find ohms just as easily. And that formula is a little friendlier, right? Just V divided by I. The point there is it doesn't matter which one you do. Do whichever one you want, right? So we're going to take our volts, 120, divided by our amps, 0.833. We get 144.058 ohms, right? So you see we've just calculated all four values for that equation pretty easily. We just did two division problems, really. I mean, with that Ohm's law wheel as reference, it's not a big deal, not a problem. So let's introduce one extra twist to all this, okay? You're going to get sick of me talking about fixed resistance as we go through this class, okay? So if we're going to operate a resistive load at a voltage other than the rated voltage, what happens to the other values? So let's back up. What's a resistive load, first of all? Something with a resistive element or filament. So an incandescent light bulb, a heating element. Those types of things are resistive loads, okay? We have, what they call an inductive load, maybe a motor load, a fluorescent ballast. Those things are kind of a different animal. Again, we're just talking about resistive loads. And I don't need you to stress over the difference between the two. But it's important to know that what we're talking about here is for resistive loads. That's kind of a simple, bare, pure circuit, as simple as we can strip it down, right? So anyway, for a resistive load, what happens if we operate it at a different voltage other than what it's rated for? What happens to the other values in the circuit, right? And by that I mean we've changed the voltage. How does that affect the amperage, the wattage, and the ohms or the resistance? Okay. And that's what we're going to look at. So fixed resistance is a key term here. Resistance is the only value inherent to the load. So what I mean by that is it doesn't matter what we do to the voltage. We are not going to change the resistance. The resistance of an incandescent lamp filament or an electric heating element is a physical property of the material. We're not going to change that by adjusting the voltage. It's fixed, right? Fixed resistance. So, one of the first things we got to think about here is rated values versus actual values. And it doesn't matter what the load is. Let's just say it's a light bulb, an incandescent light bulb. This thing is rated to operate at 120 volts, let's say in this case. If we operate it at 120 volts, it's rated to put out 60 watts, okay? But let's say in all actuality, we're only going to feed it with 110 volts, okay? What happens to the other values, okay? So I like to kind of draw a line either mentally or literally on your paper. Essentially what happens is if we operate at 120 volts, we'll get 60 watts. We're not doing that, so we're not going to get 60 watts. So essentially, these values are stuck sort of on this left-hand side, the rated values side. They're not allowed to cross this line over into the actual values side, right? Because we're not operating at 120 volts, so we're not going to get 60 watts. So what we need to do, though, is find fixed resistance, or just resistance, right? Fixed resistance just kind of reiterates the point that it's fixed. It doesn't change. What that means is our resistance is the only value that is allowed to cross that line from the rated side to the actual side. Okay, because it's fixed. Regardless of what our voltage is, it's going to be the same. So how do we find our resistance to begin with? Well, we have two values on this rated side, don't we? So let's use these two values and find resistance. Okay, so again, we're looking for ohms. We're going to the Ohm's law wheel. We have volts, we have watts. That's telling me V squared divided by P. In this case, we have to go ahead and use that squared formula. No big deal, right? So we're going to do 120 squared divided by 60. Remember, if you're using the old-fashioned calculator, we have to remember order of operations. We have to do parentheses and exponents first, multiplication and division second, add and subtract third. Exponents is a fancy way of saying squared, so we have to square that first. So 120 squared, it equals then divided by 60. Regardless, if you do that right, you should get 240 ohms. All right. So let's throw that up here in the column of rated values. And guess what? Again, that's the only thing that's allowed to cross that line. So let's go ahead and throw it in the actual column too. So now we're looking good because I have two values in the actual column. Okay. Now with those two values, I can employ Ohm's law to find the remaining values. Right? So it doesn't matter which. Let's, in this case, I want to find watts because we already know it should be 60 watts at 120, but now I'm curious what happens. We can compare that then if we only operated at 110. So let's find watts next. It doesn't matter which order you do these in. So we're looking at the actual side only. So we have V and we have R. We have volts and ohms. So we're going to do V squared divided by R. Again, remembering order of operations, we come out with 50.417 watts. Okay. And we'll go back and compare and talk about why we see the difference that we do and if it makes sense. But for the time being here, let's go ahead and find the one remaining value on the actual side. That would be current or amps. So according to our Ohm's law wheel, now we can basically use any one of these formulas we want because we have three values. In this case, I think V divided by R is a nice, easy way to do it. Again, you could do any one of those you want. That's just what I have to choose here. So we have V divided by R, 110 divided by 240. That gives us 0.458 amps. Let's go ahead and file that up here. Now, just to round it out, let's find out what the ampacity should have been over here on the rated side had we operated this thing at 120 volts, right? Again, we're looking for amps, and I'm only going to use values that are in this rated column. We're not allowed to be crossing columns here other than our fixed resistance, right? So, in this case, we're going to use V divided by R. Again, you could use any one of those formulas you wanted, but that'll be 120 divided by 240. Equals 0.5 amps, right? Nice simple math here for us. So we've got all the values in both sides. So had we operated this thing at 120 volts, we would have expected 60 watts, 240 ohms of resistance, and half an amp, 0.5 amps. How's that compare with when we operated at 110? So think about this. It's supposed to be 120. We actually operated it at slightly less voltage. We lowered the voltage. So voltage is a little bit lower. What does that do to our wattage? Hey, guess what? Wattage went down as well. We lower the voltage. We also lower the wattage. What's that do to our resistance? Well, that's literally we copied and pasted from one to the other. They will always be the same. They better be. Otherwise, we've got some major problems. Remember, fixed resistance can go from one side to the other. What's that do to our ampacity? Well, the trend continues. We lower the voltage. We're going to lower the amperage. Okay, so that's a nice check for you, too. You can tell if you did this right. If voltage went down, your watts and your amps better have gone down as well, and vice versa. If it went up, voltage went up, your watts and amps should also go up accordingly. That's, again, different. This is a resistive load. Inductive loads, you're actually going to see the opposite, right? You lower the voltage, the ampacity is going to go up to compensate, right? But in a resistive load, you're going to do this dozens of times per chapter. Please get this in your head. Fixed resistance is key. That's the only value that's allowed to cross this line. So right away, you're finding fixed resistance first, and we're going Ohm's law from there.